Classification of crystals, Part 3 of 3, Crystal Forms, Phase Intercepts and Miller Indices. A. General. The former two videos of this series dealt with the classification of crystals into systems and classes. As pointed out in the second video, the focus in this series is directed towards crystal morphology rather than internal atomic structure. In other words, the unit cell, motif, crystal lattice, etc. The term crystal form is usually given to the general external appearance of a crystal whose faces have similar space-intercept relationships with the crystallographic axis. See the first video of this series about the crystallographic axis and figures 1a to f. In this video, the intercept relationships between crystal faces and crystallographic axes and their representation by Miller indices are explained. Moreover, the face intercepts and Miller indices of some important crystal forms are described in detail. B. Face intercepts. The face intercepts denote the distances at which a face or its extension intercepts each of the crystallographic axes or their continuations. The face intercepts are usually expressed by a number of three figures, or four in the case of hexagonal system. The first figure represents the face intercepts with the A-axis, the second indicates the intercept with the B-axis, and the third denotes the intercept with the C-axis. The distance from the origin to the end point of each crystallographic axis, whether the system has 3 or 4 crystallographic axes, is considered as a unit of dimension for distance measurement along that axis. See Figure 2. Figure 2. The length from the origin O to the end of the positive side of the B-axis represents 1 unit of dimension for distance measurement along that axis. Twice this length is 2 units, and thrice this length is 3 units, and so on. The distance at which a face or its extension intercepts an axis or its continuation is expressed in terms of the unit of dimension along that axis. Since the length of the unit of dimension depends on the axis length, then when 2 or 3 crystallographic axes are equal in length, as in the cases of A1, A2, and A3 in the cubic and hexagonal systems, and A1 and A2 in the tetragonal system, the units of dimensions are identical along those axes. There are many possibilities of face-intercept relationships with the 3 crystallographic axes, such as 1. A face intercepts 1 crystallographic axis and parallel to the other 2, Figure 3. The colored face, for example, intercepts A1 axis at infinity, in other words, parallel to it, cuts A2 axis at plus A2, in other words, positive 1 unit, and parallel to the A3 axis. Thus, the intercepts of the colored face are infinity, 1, infinity. 2. A face intercepts 2 crystallographic axes and parallel to the third, Figure 4. The colored face, for example, intercepts A1 axis at 1 unit, parallel to A2 axis, and intercepts A3 axis at 1 unit. Thus, the colored face intercepts are 1, infinity, 1. 3. A face intercepts all 3 crystallographic axes, Figures 5 to 7. The colored face of Figure 7, for example, intercepts A1 axis at 1 unit, its extension intercepts the continuation of A2 axis at 1.5 units, and intersects the continuation of A3 axis at 3 units. Thus, the colored face intercepts are 1, 3 over 2, 3. The faces of a crystal form that belongs to a certain class have similar intercept relationships on the crystallographic axis, which are peculiar to that form, and that distinguish it from the other forms of the same class. However, The face intercepts of the same form differ from one face to another in the sequence and/or sign of the intercept values. Thus, the criterion of face intercepts can be used to identify a crystal form that belongs to a certain class and distinguish between its faces. Some common prefixes and suffixes in crystallography. Prefixes: mono, one or single; poly, many or much; bi, having two, twin or double; di, two or twice; tri, three; tetra, four; penta, 5; hexa, 6; hepta, 7; octa, 8; enia or nona, 9; deca, 10; hendeca, 11; dodeca, 12; icosa, 20. Suffixes: hedron, face, used in naming geometrical solids; plural, hedra; gon, angled or angular. C. Miller indices. The intercept values of a face may not be integer number. W. H. Miller proposed a method of converting the face intercepts to an indices consisting of a series of whole numbers. These numbers are derived from the intercept values by taking their reciprocals and subsequent multiplication by the lowest integer that clear off fractions if any. The positive sign of the number is usually omitted because it is evident, whereas the negative sign is written on top of the number as above. Let us study in details some important crystal forms and derive the Miller indices of some of their faces. See Table 1. Note: the Miller indices of one of the faces has been selected as typical of the form, either the front, top, or right-hand top, with positive values wherever possible. E. Study of the main forms in crystal systems and classes. 1. Isometric or cubic system. A. Hexoctahedral class. Forms: 1. Hexahedron or cube, 001; 2. Octahedron, 111; 3. Dodecahedron or rhomb-dodecahedron, 011; 4. Tetrahexahedron, 012; 5. Trapezohedron or tetragonal trisoctahedron, 112; 6. Trisoctahedron or trigonal trisoctahedron, 221; 7. Hexoctahedron, 123. 1. Isometric system. A. Hexoctahedral class. 1. Hexahedron or cube, 001. Each of the 6 square faces of the cube is parallel to 2 crystallographic axes and cuts the third at 1 unit. Figure 8. The colored face, for example, intersects a 1 axis at 1 unit parallel to a 2 axis and parallel to a 3 axis. Thus, the intercepts of the colored face can be written in the sequence A1, A2, and A3 as 1, infinity, infinity. In order to derive the Miller indices, we take the reciprocals of the face intercept values, that is, 1 over infinity, 1 over infinity, which can be written as 1, 0, 0. Since there is no fraction, then the Miller indices of the colored face remains as the face intercepts, that is, 1, 0, 0. As mentioned earlier, the faces of a form that belongs to a certain class have similar intercept relationships to the crystallographic axes, which are peculiar to that form and unlike any other form in the same class, figures 3 to 7. However, the faces of the same form differ in the sequence and/or sign of their intercept values. Thus, if the class is identified, then the intercepts of one of the faces is sufficient to identify the form. In the case of the cube, for example, the digits 0, 0, and 1 are present in the Miller indices of all the faces. However, they differ in their sequence and/or their signs. The Miller indices of the 6 faces of the cube are 1, 0, 0, minus 1, 0, 0, 0, 1, 0, 0, minus 1, 0, 0, 0, 1, and 0, 0, minus 1. See figure 9b. 1A2 octahedron 1, 1, 1. Each of the 8 equilateral triangular faces of the octahedron intercepts each of the 3 crystallographic axes at 1 unit. The colored face, figure 10a, for example, intersects A1 axis at 1 unit, A2 axis at negative 1 unit, and A3 axis at 1 unit. Thus, the intercepts of the colored face are 1, minus 1, 1. The reciprocals of the face intercept values are the same. Thus, the Miller indices remain as the face intercepts. In other words, 1, minus 1, 1. The Miller indices of the front faces of the octahedron are shown in figure 10a. Assignment 1. Write the Miller indices of the faces of the octahedron. Figure 10c. 1a3. Dodecahedron or dodecahedron 0, 1, 1. Each of the 12 home-shaped faces of the dodecahedron intersects 2 crystallographic axes at 1 unit and parallel to the third, figure 11a. The colored face, for example, parallel to the A1 axis, intersects A2 axis at 1 unit and intersects A3 axis at 1 unit. Thus, the intercepts of the colored face are infinity 1, 1. The reciprocal of the face intercept numbers are 1 over infinity 1, 1, which can be written simply as 0, 1, 1. Since there is no fraction, then the Miller indices of the colored face remain as 0, 1, 1. Assignment 2. Write the Miller indices of all the faces of the dodecahedron, figure 11b. 1a4 tetrahexahedron 0, 1, 2. Each of the 24 isosceles triangular faces of the tetrahexahedron intercepts 1 crystallographic axis at 1 unit parallel to the second axis and cuts the third axis at 2 units. Figure 12a. The colored face, for example, intersects A1 axis at 1 unit parallel to A2 axis, and its extension intersects the continuation of A3 axis at 2 units. Thus, the intercepts of the colored face are 1, infinity 2. The reciprocals of the face intercepts are 1, 1 over infinity, 1 over 2. Multiplying by 2 to clear off fraction gives the Miller indices of the colored face 2, 0, 1. Assignment 3. Write the Miller indices of the front faces of the tetrahexahedron. Figure 12c. 1a5 trapezohedron or tetragonal trisoctahedron 1, 1, 2. Each of the 24 trapezium-shaped faces of the trapezohedron intersects 1 crystallographic axis at 1 unit and each of the other 2 axes at 2 units. Figure 13. The colored face, for example, intersects A1 axis at 1 unit. Its extension intercepts the continuations of A2 axis at 2 units and A3 axis at negative 2 units. Thus, the intercept of the colored face are 1, 2, minus 2. The reciprocals of the face intercepts are 1, 1/2, minus 1/2. Multiplying by 2 to clear off fractions, we get the Miller indices of the colored face as 2, 1, minus 1. Assignment 4. Write the Miller indices of the front faces of the trapezohedron, figure 13b. 1a6 trisoctahedron or trigonal trisoctahedron 2, 2, 1. Each of the 24 isosceles triangular faces of the trisoctahedron, figure 14a, intersects 2 crystallographic axes at 1 unit and the third axis at 2 units. The colored face, for example, intersects each of the A1 and A2 axes at 1 unit and its extension cuts the continuation of A3 axis at 2 units. Thus, The intercepts of the colored face are 1, 1, 2. The reciprocal of the face intercepts are 1, 1, 1/2. Clearing of the fraction by multiplying by 2, we get the Miller indices of the colored face as 2, 2, 1. Assignment 5. Write the Miller indices of the front faces of the thrice octahedron, figure 14b. 1a, 7. Hexoctahedron, 1, 2, 3. Each of the 48 triangular faces of the hexoctahedron, figure 15a, intercepts one crystallographic axis at 1 unit, the second axis at 1.5 units, and the third axis at 3 units. The colored face, for example, intersects a one-axis at 1 unit. Its extension intersects the continuation of a 2-axis at 1.5 units and the continuation of a 3-axis at 3 units. Thus, the intercepts of the colored face are 1, 3/2, 3. The reciprocal of the face intercept values are 1, 2/3, 1/3. Clearing of fractions by multiplying by 3, the Miller indices of the colored face can be obtained as 3, 2, 1. Assignment 6. Write the Miller indices of the front faces of the hexoctahedron, figure 15b. 1. Isometric or cubic system. B. Hextetrahedral class. Forms 1. Tetrahedron 1, 1, 1 or 1, -1, 1. 2. Tristetrahedron or trigon tritetrahedron 1, 1, 2 or 1, -1, 2. 3. Deltoid dodecahedron or tetragon tritetrahedron 2, 2, 1 or 2, -2, 1. 4. Hextetrahedron or hexatetrahedron 3, 2, 1 or 3, -2, 1. 1b1. Tetrahedron 1, 1, 1 or 1, -1, 1. Each of the 4 equilateral triangular faces of the tetrahedron intercepts each of the 3 crystallographic axes at 1 unit, figure 16a. Depending on the orientation of the faces relative to the crystallographic axis, 2 forms of tetrahedron may be identified. A positive form as shown in figures 16a and b, and a negative form shown in figure 16c. In the positive form, figure 16b, the colored face intersects each of the 3 crystallographic axes, A1, A2, and A3, at 1 unit. Thus, the intercepts of the colored face are 1, 1, 1. The Miller indices obviously remain as 1, 1, 1. The Miller indices of the 4 faces are 1, 1, 1, 1, -1, -1, -1, -1, 1, and -1, 1, -1. In the negative form, figure 16c, each of the 4 faces intersects at least one negative end of the 3 crystallographic axes. Thus, the Miller indices of each of the 4 faces contain at least one negative digit. The Miller indices of the 4 faces of the negative form, figure 16c, are 1, 1, -1, 1, -1, 1, -1, -1, -1, and -1, 1, 1. A rotation of 90 degrees around one of its crystallographic axes brings the positive tetrahedron into negative position or the negative into positive position, figures 17a to d. Assignment 7. Write the Miller indices of the faces of the 2 types of tetrahedrons, figures 17c and d. 1b2. Tristetrahedron or trigon tritetrahedron 1, 1, 2 or 1, -1, 2. Each of the 12 isosceles triangular faces of the tristetrahedron, figure 18a, intersects 2 crystallographic axes at 2 units and the third axis at 1 unit. The colored face or its extension, figure 18b for example, intersects each of the continuations of A1 and A2 axes at 2 units and the A3 axis at 1 unit. Thus, the intercepts of the colored face are 2, 2, 1. Taking the reciprocals of the face intercept digits and clearing off the fractions by multiplying by 2, the Miller indices turn out to be 1, 1, 2. Depending on the orientation of the faces relative to the crystallographic axis, two forms of the thrice tetrahedron may be recognized. A positive form shown in figures 18a, b, c, and e, and a negative form shown in figures 18d and f. A rotation of 90 degrees around one of the crystallographic axes brings the positive form into negative position or the negative into positive position. Figures 18c to f. Assignment 8. Write the Miller indices of the faces of the positive and negative thrice tetrahedrons of figures 18e and f. 1b3. Deltoid dodecahedron or tetragon tritetrahedron. 2, 2, 1 or 2, minus 2, 1. Each of the 12 tetragonal faces of the deltoid dodecahedron intersects two crystallographic axes at 1 unit and the third axis at 2 units. The colored face, figure 19a for example, cuts each of the A1 and A2 axes at 1 unit and its extension intersects the continuation of A3 axis at 2 units. Thus, the intercepts of the colored face are 1, 1, 2. Taking the reciprocal of the face intercepts, multiplying by 2 to clear off the fraction, the Miller indices of the colored face become 2, 2, 1. There are two forms of the deltoid dodecahedron depending on the orientation of the faces relative to the crystallographic axis. A positive form shown in figures 19b and d, and a negative form shown in figures 19c and e. A rotation of 90 degrees around one of the crystallographic axes of the deltoid dodecahedron brings the positive form into negative position or vice versa. Figures 19b to e. Assignment 9. Write the Miller indices of the front faces of the positive and negative deltoid dodecahedron of figures 19d and e. 1b4 hextetrahedron or hexatetrahedron. 3, 2, 1 or 3, minus 2, 1. Each of the 24 triangular faces of the hextetrahedron, figure 20a, intercepts one crystallographic axis at 1 unit, the second axis at 1.5 units, and the third axis at 3 units. The colored face, for example, intersects A1 axis at 1 unit, and its extension intersects the continuations of A2 axis at 1.5 units and A3 axis at 3 units. Thus, the intercepts of the colored face are 1, 3 over 2, 3. Taking the reciprocal of the face intercepts, multiplying by 3 to clear off the fractions, we get the Miller indices of the colored face as 3, 2, 1. There are two types of hextetrahedra depending on the orientation of its faces relative to the crystallographic axis, positive and negative. A positive form shown in figure 20b and a negative form shown in figure 20c. A rotation of 90 degrees around one of the crystallographic axes of the hextetrahedron brings the positive form into negative position or the negative form into positive position. Figures 20b and c. Assignment 10. Write the Miller indices of the front faces of the positive and negative forms of the hextetrahedron of figures 20b and c. 1. Isometric or a cubic system. C. Diploidal class. Forms 1. Pyritohedron 1, 0, 2. 2. Diploid 3, 2, 1. 1. C1 Pyritohedron 1, 0, 2. Each of the 12 pentagonal faces of the pyritohedron intersects one crystallographic axis at 1 unit, parallel to the second, and cuts the third axis at 2 units. Figure 21a. The colored face, for example, intersects a 1 axis at 1 unit. Its extension cuts the continuation of a 2 axis at 2 units, and it is parallel to the A3 axis. Thus, the intercepts of the colored face are 1, 2, infinity. Taking the reciprocal of the face intercepts, multiplying by 2 to clear off the fraction, we get the Miller indices of the colored face as 2, 1, 0. Depending on the orientation of its faces relative to the crystallographic axis, two forms of the pyritohedron may be identified, positive and negative, figures 21b to e. A rotation of 90 degrees around one of its crystallographic axes brings the positive pyritohedron into negative position, or vice versa, figures 21b to e. Assignment 11. Write the Miller indices of the front faces of the positive and negative forms of the pyritohedron, figures 21, D and E. 1, C, 2. Diploid, 3, 2, 1. Each of the 24 tetragonal faces of the diploid, figures 22A to D, intercepts one crystallographic axis at 1 unit, the second axis at 1.5 units, and the third axis at 3 units. The colored face of figure 22A, for example, intersects A1 axis at 1 unit, and its extensions intersect the continuations of A2 axis at 1.5 units and A3 axis at 3 units. Thus, the intercepts of the colored face are 1, 3 over 2, 3. Taking the reciprocal of the face intercepts, multiplying by 3 to clear off fractions, the Miller indices of the colored face turn out to be 3, 2, 1. There are two forms of the diploid depending on the orientation of its faces relative to the crystallographic axis, positive and negative, figures 22b to d. A rotation of 90 degrees around one of its crystallographic axes brings the positive diploid, figure 22c, into negative position, figure 22d, or the negative form into positive position. Assignment 12. Write the Miller indices of the front faces of the positive and negative forms of the diploid, figures 22c and 22d. 2. Hexagonal system. A. Dihexagonal dipyramidal class. Forms 1. Pinacoid 0, 0, 0, 1. 2. A. Hexagonal prism 1, 0, minus 1, 0. 2. B. Hexagonal prism 1, 1, minus 2, 0. 3. A. Hexagonal dipyramid 1, 0, minus 1, 1. 3. B. Hexagonal dipyramid 1, 1, minus 2, 2. Hexagonal system. General. In the hexagonal system, where there are 4 instead of 3 crystallographic axes, the face intercepts are expressed as a series of 4 numbers. The first 3 figures denote the intercepts with the A1, A2, and A3 axes respectively, and the fourth indicates the intercepts with the C axis. In the hexagonal system, a face may intersect A. one crystallographic axis and parallel to the other 3, for example, the colored face of figure 23A. B. 2 crystallographic axes and parallel to the other 2, for example, the colored face of figure 23B. C. 3 crystallographic axes and parallel to the fourth, for example, the colored face of figure 23C. D. All the crystallographic axes, for example, the colored face of figure 23D. Some forms, such as prisms, are open, and thus requires additional faces of different characteristics to close it. A pinacoid or parallelohedron, which is an open form, also consists of 2 parallel faces, combines with 1 or more open forms to create a closed one. In the case of a hexagonal prism, for example, a pinacoid cuts the prism at top at plus C and bottom at minus C, and parallel to the 3 horizontal axes, combines with the prism and create a closed combination of 2 forms. For example, figures 23A, 23B, 24, etc. 2A1 pinacoid 0001. The top and bottom faces, figure 24, are parallel to the three horizontal axes. The top face intersects the c-axis at its positive end, and the bottom face intersects the c-axis at its negative end. The pinacoid combines with the prism and converts it to a closed form. The intercepts of the colored face of the pinacoid, for example, are infinity, infinity, infinity 1. From the reciprocal of the intercepts, the Miller indices become 0, 0, 0, 1. 2A, 2A, hexagonal prism, 1, 0, minus 1, 0. Each of the 6 vertical faces of the hexagonal prism, figure 25A, intercepts 2 of the 3 horizontal crystallographic axes at 1 unit, parallel to the third and parallel to the c-axis. The colored face, for example, parallel to the A1 axis, cuts A2 axis at 1 unit, intersects A3 axis at negative 1 unit, and parallel to the c-axis. Thus, the intercepts of the colored face are infinity, 1, minus 1, infinity. By taking the reciprocal of the face intercepts, the Miller indices of the colored face become 0, 1, minus 1, 0. Assignment 13. Write the Miller indices of the faces of the hexagonal prism 1, 0, minus 1, 0 and basal pinacoid of figure 25b. 2A, 2B, hexagonal prism 1, 1, minus 2, 0. Each of the 6 vertical faces of the hexagonal prism 1, 1, minus 2, 0 intersects 1 horizontal crystallographic axis at 1 unit. Its extension cuts the continuations of the other 2 axes, each at 2 units and parallel to the c-axis, figure 26a. The colored face, for example, cuts the continuations of each of the A1 and A2 axes at 2 units, cuts the A3 axis at negative 1 unit and parallel to the c-axis. Thus, the intercepts of the colored face are 2, 2, minus 1, infinity. By inverting the face intercept values, multiplying by 2 to clear off fractions, the Miller indices of the colored face can be found as 1, 1, minus 2, 0. Assignment 14. Write the Miller indices of the faces of the hexagonal prism 1, 1, minus 2, 0 and basal pinacoid of figure 26b. 2A, 3A, hexagonal dipyramid 1, 0, minus 1, 1. Each of the 12 isosceles triangular faces of the hexagonal dipyramid 1, 0, minus 1, 1, figure 27a, intersects 2 of the 3 horizontal crystallographic axes at 1 unit, parallel to the third, and cuts the fourth vertical axis at 1 unit. The colored face, for example, parallel to the A1 axis, cuts the A2 axis at 1 unit, intersects A3 axis at negative 1 unit, and intersects the C axis at negative 1 unit. Thus, the intercepts of the colored face are infinity, 1, minus 1, minus 1, from which the Miller indices become 0, 1, minus 1, minus 1. Assignment 15. Write the Miller indices of the faces of the hexagonal dipyramid 1, 0, minus 1, 1 of figure 27c. 2A, 3B, hexagonal dipyramid 1, 1, minus 2, 2. Each of the 12 isosceles triangular faces of the hexagonal dipyramid 1, 1, minus 2, 2 intersects all the 4 crystallographic axes. It cuts 2 horizontal axes at 2 units, the third at 1 unit, and the c-axis at 1 unit, figure 28a. The colored face, for example, cuts the continuation of A1 and A2 axes, each at 2 units, the A3 axis at negative 1 unit, and the c-axis at negative 1 unit. Thus, the intercepts of the colored face are 2, 2, minus 1, minus 1. Multiplying the reciprocal of the face intercepts by 2 to clear off the fractions, we get the Miller indices of the colored face as 1, 1, minus 2, minus 2. Assignment 16. Write the Miller indices of the faces of the hexagonal dipyramid 1, 1, minus 2, 2 of figure 28b. 3. Tetragonal system. A. Ditetragonal dipyramidal class. Forms 1. Basal pinacoid 0, 0, 1. 2. A. Tetragonal prism 0, 1, 0. 2. B. Tetragonal prism 1, 1, 0. 3. A. Tetragonal dipyramid 1, 1, 1. 3. B. Tetragonal dipyramid 0, 1, 1. 3. A. 1. Basal pinacoid 0, 0, 1. As pointed out in discussing the hexagonal system, some forms, such as prisms, are open. A pinacoid, which consists of two parallel faces, combines with one or more open forms and create a closed combination form. In the case of a tetragonal prism, for example, a pinacoid intercepts the prism at top plus C and bottom minus C, and parallel to the two horizontal axes, converts the prism to a closed combination form, figures 29 to 31. 3A, 2A, tetragonal prism 1, 1, 0, also known as first order prism. Each of the four rectangular faces of the tetragonal prism 1, 1, 0 cuts each of the two horizontal crystallographic axes at one unit and parallel to the C-axis. The front right-hand face, figure 30A, for example, intersects A1 and A2 axes each at one unit and parallel to the C-axis. Thus, the face intercepts are 1, 1, infinity. Hence, the Miller indices become 1, 1, 0. Three A, 2B, tetragonal prism 0, 1, 0, also known as second order prism. Each of the four rectangular faces of the tetragonal prism 0, 1, 0 cuts one horizontal crystallographic axis at one unit parallel to the second and parallel to the C-axis. The front face, figure 31A, for example, intercepts A1 axis at one unit and parallel to both A2 and C axes. Thus, the intercepts of the front face are 1, infinity, infinity. Hence, the Miller indices become 1, 0, 0. Note that the top and bottom faces belong to the basal pinacoid 0, 0, 1. Three A, tetragonal dipyramid 1, 1, 1, also known as first order pyramid. Each of the 8 isosceles triangular faces of the tetragonal dipyramid cuts each of the 3 crystallographic axes at one unit. The top right-hand front face, for example, figure 32A, intersects A1 and A2 axes, each at one unit, and cuts the C-axis at one unit also. Thus, the intercepts of the top right-hand front face may be written as 1, 1, 1. Accordingly, the Miller indices are 1, 1, 1 also. 3A, 3B, tetragonal dipyramid 0, 1, 1, also known as second order pyramid. Each of the 8 isosceles triangular faces of the tetragonal dipyramid 0, 1, 1 cuts one horizontal crystallographic axis at one unit parallel to the second and cuts the C-axis at one unit. The top front face, figure 33A, for example, intersects A1 axis at one unit parallel to the A2 axis and cuts the C-axis at one unit. Thus, the intercepts of the top front face are 1, infinity, 1. Accordingly, the Miller indices are 1, 0, 1. 4. Orthorhombic system. A. Rhombic dipyramidal class. Forms 1. Pinacoids 1, 0, 0, 0, 1, 0, and 0, 0, 1. 2A. Rhombic prism 1, 1, 0. 2B. Rhombic prism 1, 0, 1. 2C. Rhombic prism 0, 1, 1. 3. Rhombic dipyramid 1, 1, 1. 4. A1 pinacoids 1, 0, 0, 0, 1, 0, and 0, 0, 1. Figures 34A to C show a combination of A macropinacoid 1, 0, 0, a pinacoid or parallelohedron whose two parallel faces, each of which intersects the A-axis at plus A and minus A and parallel to the B and C axes. B. Brachypinacoid 0, 1, 0, a pinacoid whose two parallel faces, each of which intersects the B axis at plus B and minus B and parallel to the A and C axes. And C. Basal pinacoid 0, 0, 1, each of its two parallel faces cuts the C axis at plus C and minus C and parallel to the two horizontal axes. 4. A, 2A, rhombic prism 1, 1, 0. The rhombic prism 1, 1, 0 consists of the four faces 1, 1, 0, 1, minus 1, 0, minus 1, minus 1, 0, and minus 1, 1, 0. It combines with the basal pinacoid that consists of the two faces 0, 0, 1 and 0, 0, minus 1 to create a closed form. Figure 35A. 4A, 2B, rhombic prism 1, 0, 1. The rhombic prism 1, 0, 1 consists of the four faces 1, 0, 1, 1, 0, minus 1, minus 1, 0, minus 1, and minus 1, 0, 1. It combines with the side pinacoid that consists of the two faces 0, 1, 0, and 0, minus 1, 0 to create a closed form. Figure 35B. 4A, 2C, rhombic prism 0, 1, 1. The rhombic prism 0, 1, 1 consists of the four faces 0, 1, 1, 0, 1, minus 1, 0, minus 1, minus 1, and 0, minus 1, 1. It combines with the front pinacoid that consists of the two faces 1, 0, 0, and minus 1, 0, 0 to create a closed form. Figure 35C. 4A3, rhombic dipyramid 1, 1, 1. Each of the 8 triangular faces of the rhombic dipyramid 1, 1, 1 cuts each of the 3 crystallographic axes at 1 unit. The top right-hand front face, figure 36A for example, intersects A, B, and C axes each at 1 unit. Thus, the intercepts of the top right-hand front face may be written as 1, 1, 1. Obviously, the Miller indices remain the same. That is to say, 1, 1, 1. 5. Monoclinic system. A. Prismatic class. Forms 1. Prisms 1, 1, 0, 1, 0, 1, and 0, 1, 1. 2. Pinacoids 1, 0, 0, 0, 1, 0, and 0, 0, 1. 3. Combination of 4 pinacoids. 5A, 1A, prism 1, 1, 0. The monoclinic prism 1, 1, 0 of this class consists of 4 faces 1, 1, 0, 1, minus 1, 0, minus 1, minus 1, 0, and minus 1, 1, 0. It combines with a basal pinacoid 0, 0, 1 and 0, 0, minus 1 to make a closed form. Figure 37A. 5A, 1B, prism 1, 0, 1. The monoclinic prism 1, 0, 1 consists of 4 faces 1, 0, 1, 1, 0, minus 1, minus 1, 0, minus 1, and minus 1, 0, 1. It combines with the side pinacoid 0, 1, 0 and 0, minus 1, 0 to make a closed form. Figure 37B. 5A, 1C, prism 0, 1, 1. The monoclinic prism 0, 1, 1 consists of 4 faces 0, 1, 1, 0, 1, minus 1, 0, minus 1, minus 1, and 0, minus 1, 1. It combines with the front pinacoid 1, 0, 0 and minus 1, 0, 0 to make a closed form, figure 37c. 5a2. Pinacoids 1, 0, 0, 0, 1, 0 and 0, 0, 1. Figure 38 shows a combination of pinacoids, front 1, 0, 0 and minus 1, 0, 0, side 0, 1, 0 and 0, minus 1, 0, and base 0, 0, 1 and 0, 0, minus 1. 5a3. Combination of 4 pinacoids. This form, figure 39a, may be considered as a combination of 4 pinacoids, each of which intersects the 3 crystallographic axes. Positive right 1, 1, 1 and minus 1, minus 1, minus 1, figure 39b. Positive left 1, minus 1, 1 and minus 1, 1, minus 1, figure 39c. Negative right minus 1, 1, 1 and 1, minus 1, minus 1, figure 39d, and negative left minus 1, minus 1, 1 and 1, 1, minus 1, figure 39e. Note, the above form was also considered as a combination of 2 open forms, each of which consists of 4 triangular faces, all of which intersects the 3 crystallographic axes. A pyramid of the first type 1, 1, 1, figure 39f, and a pyramid of the second type minus 1, 1, 1, figure 39g, combine to make a pyramid of a closed form, figure 39h. 6. Triclinic system. A. Pinacoidal class. Forms pinacoids 1, 0, 0, 0, 1, 0 and 0, 0, 1. 6a. Pinacoids 1, 0, 0, 0, 1, 0 and 0, 0, 1. Figure 40 shows a combination of pinacoids, front 1, 0, 0 and minus 1, 0, 0, side 0, 1, 0 and 0, minus 1, 0, and base 0, 0, 1 and 0, 0, minus 1. Figures 41 to 44 show different types of triclinic pinacoids and the possibility of considering each type as a combination of different alternative forms. Figure 41. Triclinic pinacoids. Positive 1, 0, 1 and minus 1, 0, minus 1. Negative 1, 0, minus 1 and minus 1, 0, 1. And side 0, 1, 0 and 0, minus 1, 0. Note, it may also be considered as a combination of prism 1, 0, 1, 1, 0, minus 1, minus 1, 0, minus 1, and minus 1, 0, 1, and side pinacoid 0, 1, 0, and 0, minus 1, 0. Figure 42. Triclinic pinacoids. Positive 0, 1, 1, and 0, minus 1, minus 1, and negative 0, minus 1, 1, and 0, 1, minus 1, combined with a front pinacoid 1, 0, 0, and minus 1, 0, 0. Note, it may also be considered as a combination of prism 0, 1, 1, 0, 1, minus 1, 0, minus 1, minus 1, and 0, minus 1, 1, and front pinacoid 1, 0, 0, and minus 1, 0, 0. Figure 43. Combination of 4 different pinacoids, each of which intersects all the 3 crystallographic axes. See the details in the following figures. Note, it was also considered as a triclinic pyramid that consists of 4 pyramidal units, each of which lies in 2 of the 8 octants. I hope you have benefited from this series of videos and gained a practical knowledge that helps in studying crystallography and identify the systems, classes, and forms of crystals.